Hello, my name is Said Zendegan and I'm a project assistant in TU Wien in Institute for Mechanics and Mechatronics. I work in project Hydrogen Truck Austria, HyTruck. HyTruck project is an FFG funded project which AVLIS GmbH is the coordinator of this project. Project goal is to develop, build, calibrate and validate a heavy-duty fuel cell powertrain which fulfills the requirements regarding power, efficiency, reliability and lifetime. And in order to do that, we develop new and innovative control strategies to improve the performance of the entire vehicle. TU Wien is responsible for operation and control of HT applications. We here investigate the integration of the predictive information into the energy management system to assess the potential improvements in hydrogen consumption and fuel cell system lifetime and also battery system lifetime. For the electrification of the road freight transport system, there are two options: fuel cell vehicles and pure battery vehicles. However, based on the characteristics of the fuel cell systems seem a better option, which are zero emissions and a higher energy density of the hydrogen and fast refueling time, which are advantages over the pure battery vehicles. However, there are some issues. Cost is high, system lifetime is low, and H2 infrastructures are still missing. By the way, the fuel cell electric vehicle architecture is consisting of battery and a fuel cell system, which are supposed to deliver the electric power demand, which are done by an energy management system. Energy management system is a necessary system to define the set points for these subsystems in the powertrain, which will define the set points for fuel cell and battery. Our energy management targets are maximizing hydrogen economy, mitigating fuel cell degradation, and mitigating battery degradation. In order to maximize the hydrogen economy, we tend to operate the fuel cell in high efficiency region. To lower down the system degradation for the fuel cell, we avoid frequent shutdowns and limit the low and high power operation, and also decrease the system dynamics, which are all of them together are main sources of the system degradation. However, for the battery system, we also need to consider system lifetime. To do so, we operate the battery in a prescribed region. To use the predictive information in our energy management is the goal to improve the performance of the entire vehicle. We tend to use the predictive information and to improve the performance of the energy management strategy in order to improve the overall performance of the vehicle. One of the predictive information would be the long-term information. When the driver chooses his destination, onboard GPS systems could provide us a road elevation, speed limits, road gradient, which can be very useful when we are designing our energy management strategy. Imagine a truck traveling over this schematic road. A truck will have high power demand region and also will pass through the high available kinetic energy regions. If we want to improve the performance of this vehicle, we need to consider these sections. However, to do so, we tend to generate reference signals for the battery systems in order to improve the entire vehicle performance. The motivations to generate these reference signals is to avoid overcharge and complete discharge. For example, in uphills, if we have low SOC, which is a battery state of charge, we may run into a completely discharged battery when the power demand is really high. And when we are coming down the downhills and our SOC level is high, we may not recuperate as much as possible, and the rest of the energy will be wasted in the mechanical brakes. However, to do with generating SOC reference signals and influencing the battery behavior, we tend to influence also the fuel cell behavior and overall improve the performance of the vehicle. In bottom right, you could see the elevation profile of this schematic road and a corresponding SOC profile. At first, fuel cell tends to charge the battery. So when the next section there is an uphill coming, fuel cell will be aided by battery and battery will discharge itself. However, later on in the downhill section, battery will use the kinetic energy and recharge itself. In order to generate a reference signal, we need to estimate the future load of the vehicle. To do so, we use the navigation system to get the information of the future trip, including speed limits, road gradient, and elevation. Later on, we use a vehicle model to estimate the future load based on the basic information that's provided by us by the GPS system, for example. On the right, you could see the load profile of this schematic drive cycle. But how these references are generated from the estimated electric load? There are many literature which use rule-based strategies or optimization-based strategies to generate such reference signals. However, we tend to use the optimization-based reference generation to avoid the inefficient calibration and also time-consuming efforts for the rule-based strategies. To do so, we use the open circuit battery model and use the SOC rate and relate it to the battery power. In addition to that, we define a constraint which electric load should be always delivered by the fuel cell and the battery. In addition to that, we use a fuel cell map which relates the fuel cell efficiency to the system power. In right, there is the GPS data of a sample drive cycle, speed limits and road profile. Using that and our vehicle model, we estimate the future electric load, which is depicted by the blue line. However, to use that electric load in an optimization problem, we will end up in a high complex problem which will have a high computation cost. In order to avoid that, we do some simplifications. We average the electric load in defined segments over the drive cycle. And then we also discretize the SOC rate equation and relate the delta SOC to the fuel cell power. Using the fuel cell power operation in different operation point, we can calculate the delta SOC in each segment. When fuel cell is operating at maximum and minimum power, we can calculate delta SOC in the highest and lowest operational point of the fuel cell, which is depicted by the blue and red line. And when the fuel cell is operated in the highest efficiency point, we obtain the green line. Later on, we define a quadratic cost and optimize it over the entire drive cycle, considering the system constraints. And afterwards, we obtain the desired delta SOCs, which are depicted by the gray line. We use the delta SOCs obtained in each segment and synthesize the SOC reference signal for the entire drive cycle. We have developed a simulation framework to investigate the performance of our strategy. We use simple models in the MATLAB to design our energy management strategy, and also later on we use the AVL Cruise-M, which uses a more sophisticated vehicle model to test and validate our strategy. We use real-world driving cycles to design a robust energy management strategy. And in this driving cycles, we have 140,000 kilometers of driving distance, and also these driving cycles include log speed and elevation and GPS data, which you could see in the right side, the map, which shows mostly the Central Europe. And also the vehicle masses were variable. Each vehicle had its own mass, which makes a really realistic scenario for the energy management strategy design. We would like to make a comparison between the strategy that uses the constant SOC reference and the strategy that uses a predictive SOC reference, which is our state of the art. And the control law for this rule-based strategy is defined as fuel cell set point to try to keep the fuel cell as close as possible to its highest efficiency point, and then the compensations regarding the deviation from the electric load and the reference signal for the SOC. Here is the performance evaluation of our strategy using a sample drive cycle. In the left, you can see the drive cycle data, which is the speed and the elevation. And in the bottom, there is a table of results regarding the charge sustaining and predictive strategy. Charge sustaining strategy uses the constant reference signal. On the other hand, predictive strategy uses the predictive references. You can see that the predictive strategy has significantly improved the fuel economy. And in addition to that, we have a good tracking of the SOC reference signal. And as we have generated the references in a prescribed region and we are tracking them closely, we have obtained two of our goals for the energy management strategy, which is a good SOC control and improved fuel economy. And thirdly, we also have improved the fuel cell system lifetime by operating it in lower power and avoiding unnecessary high power operation of the fuel cell system by using the predictive strategy. However, in order to show the overall performance of our strategy, we need to use the entire drive cycles and show the overall gain using the predictive method. In the table, there is a charge sustaining strategy and also the predictive strategies results. And also in the third line, there is the result coming from the PMP. PMP stands for the Pontryagin minimum principle, which in theory delivers us the global optimum of the fuel consumption, but it is an offline strategy which requires the knowledge of the entire drive cycle a priori, but it can provide us a good benchmark to evaluate the performance of our strategy. You can see that the fuel consumption with the predictive strategy is significantly better than the charge sustaining, and it is very close to the results obtained by the PMP. Battery equivalent cycle using both online strategies, charge sustaining and predictive, is in a similar range and relatively low, and the effect of this methodology can be neglected on the system lifetime of the battery. However, predictive strategy has remarkably improved the fuel cell operation by decreasing the high power operation time by 75%, which will end up in a better system lifetime. And also deviations of the SOC reference in a desirable range, which shows that we have a good control over the SOC profile. In the right, in the right top, you can see that the normalized fuel consumption using the different strategies. They are normalized using the PMP results. Using the predictive strategy, we tend to obtain quite a good fuel economy. However, by the charge sustaining strategy, in some specific drive cycles, we have a very poor fuel economy, which shows that using the predictive strategy, we can always improve the fuel economy. And if we also have a fleet of trucks and using the predictive strategy as the energy management strategy, we can always have advantages over a charge sustaining method. And also predictive strategy significantly lowers down the high fuel cell operation time in each individual cycles, which also improves the system lifetime. In addition to that, it shows that we have operated the battery in a described region using both strategies, predictive and charge sustaining strategy. And also you can see that the predictive strategy has delivered the final battery SOC very close to the initial battery SOC, which was 65%. This shows that the good capability of the charge sustaining. In the bottom, you can see the histogram plot of the fuel cell operation over the entire drive cycles, which were shown in the GPS map in the previous slides. You can see that the predictive strategy has significantly and effectively improved the fuel cell lifetime by decreasing the high operation time of the fuel cell. This is our energy management team. You could see the Professor Yakubek and Professor Hametna in a supervising level, and me, Said Zendegan, project assistant, and my colleague Alessandro Furara, university assistant, in the technical level. If you are interested, if you have any question, please do not hesitate to contact us.